My name is Sam Procter. I am the initiative lead for the Model-Based Engineering Group here at the Software Engineering Institute. Today I'm going to be talking about how the Architecture Analysis and Design Language, or AADL, helps us transition research ideas into practice. So this is a roadmap of where we're going today. We're going to be talking about the problem space that I work in, how AADL helps my teammates and I solve those problems. The DoD's recognized that, and we have seen some success in DoD projects. And then we'll wrap up by talking about how AADL aligns with DoD's digital engineering strategy. So let's talk about safety-critical embedded software systems, which is sort of a mouthful. But these are basically cyber-physical systems that, if they fail, are going to cause some sort of unacceptable loss. So think medical devices, aviation, certain automotive components, things that might cause a mission failure or an unacceptable amount of money to be lost, or even injury or death to a human if they go wrong. These systems are built in such a way that often issues are created sort of early on and caught later on. So issues are created in the requirements phase or when components are being designed, but then those issues aren't discovered until until the components are actually integrated together or the requirements are being tested. So the idea is to discover system level issues early by annotating components and then virtually integrating those components. Our solution has two prongs to it. We have a language, AADL, which is internationally standardized, so it's not something that we've just come up with in a research project and are going to abandon. It has over 15 years of use in academia and in industry. Then at the SEI, we also developed tooling to support that language. We created an integrated development environment called OSATE, or the Open Source Architecture Tool Environment, OSATE. And OSATE helps system designers write AADL, and then once you have an AADL model, helps them analyze it for various system level things. So you can attach component level latencies to your individual components and come up with an end-to-end latency once you have the system specified. So I'm generally uncomfortable talking about AADL without giving at least a flavor of it. So first we're going to give a short overview of AADL itself. AADL has two syntaxes, a graphical and a textual one. And the graphical syntax is what we're going to be using in these slides, though if you're a computer scientist like me, you might find the textual one, which is declarative in nature, a little bit more comfortable. Its graphical syntax, though, presents boxes and lines, just like engineers are drawing on whiteboards all around the world. The difference between the boxes that AADL lets you draw and those that are drawn on a whiteboard is that the semantics are precisely specified for AADL. Using mathematical descriptions, we know exactly what they mean. So, for example, this box on the slide now is a temperature control process that might be used in something like a smart building to keep a room at a comfortable temperature using a computer to govern whether or not we need to turn on a fan. As a process, it is a protected region of memory, and we can allocate threads there. Now, it's likely that if you were just drawing this on a whiteboard, you could say all of that if you were well-versed in system design issues, but what's the likelihood that someone looking at the whiteboard later on would come up with the exact same definition of a process that you would? Maybe not as high as we would hope. So that's the importance of standardizing the precise specifications of meaning that AADL enables. So we can put some threads in our process, something for a temperature sensor, a thermometer, something for a controller, a little bit of computational logic to say if the temperature is out of bounds or not, we should turn on a fan or not. And I promised you some lines, so now we can draw lines between those boxes. We can connect these threads, in this case, together with different types of intra-process communication, but we need to differentiate some of the behavior of our threads. This is where we can use AADL's extensible property mechanism, which lets us specify additional semantics to attach to various components and connections. AADL comes with a number of properties, but if you find that there aren't enough, it's easy to come up with your own properties and then use those to guide additional system analyses or code generation. In this case, we'll talk about the dispatch semantics and how those would be added with a property. Our temperature sensor is a thread that should wake up periodically and check if our room in our smart building is at a comfortable temperature. It will forward that temperature to the controller, which can decide whether or not, according to some configuration, that temperature is acceptable or not. If it is acceptable, then we don't need to do anything, but if it's not acceptable, we can turn on the fan. So what's key here is the temperature sensor needs to have what we call periodic dispatch semantics. That is, that the sensor should check according to some clock. Every once in a while, without any external interaction, it should just check the temperature. The fan, however, should only be turned on or off when the controller says it should be turned on or off, that is, using sporadic dispatch semantics. If we were to use periodic semantics for the fan, we would have a problem because the fan would turn on and off at the same rate, whether it was a hot day or a cold day, and our room probably wouldn't be very comfortable. So it's this sort of notion that we need to embed, and we can do that using AADL and the property specification mechanism. So that is the world's quickest overview of AADL, but I hope that it gives sort of a flavor for the language, because now we're going to shift gears a little bit and talk about how AADL helps us solve problems, how we use those formal specifications of developer intent to learn system level things, having annotated only the components in a system. So I'm one of the PIs on the Integrated Safety and Security Engineering project, also called ICE. And like the overall approach that we take in the model-based engineering initiative, we have a two-pronged solution here with tooling and language extensions. These are some of the high-level tasks that we did as part of the ICE project. You can see that there are several of them, mostly tooling extensions, but also some modifications to AADL itself, like a new annex to the core language that lets system designers annotate their security requirements and how their system is going to go ahead and meet those requirements. But we can also talk about the various tooling aspects. Some of these are pretty stable, like descriptions of the library of error models that we have. The error model v2 library there on the left is maybe one of the more stable tooling artifacts that was produced as part of the ICE project. On the other end is the architecture supported audit processor, which is, or ASAP, which is very much a prototype, but we think is a really exciting concept for the future of hazard analysis. So these different tasks, unfortunately, I don't have time to go into in great detail, but just to give a flavor of the type of work being done in this project, we can talk about the safety patterns. So the safety patterns task was headed up by a colleague of mine named Jerome Hugh, and the idea here is that there are a number of safety patterns that have been published in the literature, things that you should do if you want certain safety characteristics in your system architecture. So for example, if you want some part of your system to be immune to a single point of failure, you might use what's called the triple modular redundancy pattern, where you have 3 sensors and they vote. So if one of the sensors fails, the other 2 can outvote it and you'll still have correct sensor data. Unfortunately, achieving triple modular redundancy is not as straightforward as just getting 3 sensors and hooking them all together. You have to be pretty careful about how everything is configured, or you can still be vulnerable to a single point of failure. So what Jerome did was, using previous research projects, or the output of a previous research project called Architecture-Led System Assurance, he actually specified how triple modular redundancy architecture should look in AADL. And then those AADL models were embedded using an example mechanism into OSATE, the open source architecture tool environment, or SEI tooling for AADL. So now if you download OSATE, you can get the safety patterns shipped with it. That's available right now. Other research projects previously studied how to model errors in your system. That's the EMV2, and this was not done as part of ICE, but rather we built on it in this project. That's actually sort of a theme that I want to highlight, is that there has been a history of architecturally integrated safety and security work that has been done here at the SEI and then embedded into AADL and OSATE. So as you can see, in 2006, which is shortly after the original version of AADL was published, we noticed that users wanted to extend the notion of their component interface to include what we call off-nominal or rainy day behaviors. The idea here is that if I've described my sensor using AADL, I should be able to describe the various ways that it might fail. That way, when I compose my system, I can think about how that sensor failure might impact the overall system's ability to do its job. This research is actually already transitioning to practice. As you can see, we revised the error model and totally overhauled it in 2014, and now multiple contractors in the Joint Multi-Role Mission System Architecture Demonstration Program, or JMR-IMSAD, are using AADL in addition to the EMV2 Annex to describe various system components. And they're able to do this because this work was described in an annex to the core AADL language and supported via our open source tooling, OSATE. So they don't have to go out and read my paper, they don't have to go out and read Jerome's paper or the publication of any of our colleagues. They can get this knowledge just by downloading our tooling. As you can see, the safety work continues, and in the future we're going to be looking at increasingly autonomous systems and how we might model the various ways that things might go wrong so that we can think about how to make those systems safer too. Safety is only one line of research, though, that has been conducted using AADL. This is a more holistic view of the lines of research enabled by AADL. And it's not that AADL is key to, say, code generation research or behavior, but rather that AADL works with code generation technology. So if someone publishes a cool idea on code generation or requirement specification or maybe resource budgeting and latency, that idea then can be embedded in AADL. The algorithms that are developed can be encoded in OSATE. And so then downloading this tool, OSATE, using AADL as a language lets you get access to this research. And so we've seen a number of projects in DoD projects are shown here in blue, non-DoD projects in green, use various research ideas by using AADL and OSATE. So we've had users, of course, within the DoD that we're going to talk about more, but also groups like the European Space Agency, the Food and Drug Administration here in the US, a number of organizations that work with safety critical systems have found value in AADL's encoding of various research ideas. So let's talk a little bit more about that DoD impact. Specifically, I want to be sure and highlight the story of Army Aviation, because we have really had this tremendous partnership with the U.S. Army. If you were at the research review here at the SEI in 2019, you would have seen a presentation that I gave jointly with Alex Boydston, who works with the U.S. Army, and he talked about the benefits of AADL and ACVIP, or the Architecture-Centric Virtual Integration Process, which really is the process by which we say this is a good way or the correct way to use AADL to specify components and virtually integrate them. It's that architecture-centric virtual integration that I mentioned early on in this presentation. So Alex and the Army have found that there are a number of benefits to AADL and the ACVIP process that let you find problems early, let you reduce risk, and also, like we studied in the IC project, increase cybersecurity, because there are fewer gaps in the understanding of a system than you might have if you write your requirements out using narrative English. So this is particularly important in things like aviation, or in domains like aviation, because certification plays such a huge role in getting these systems built and getting them fielded. And so certification authorities, of course, appreciate unambiguous statements. So these unambiguous statements in languages like AADL can support certification for airworthiness, safety, cybersecurity, and things like that. It's not just the Army that has found these benefits, though. One of the key research projects that we built on in IC was DARPA's Hackams project, or the High Assurance Cyber Military Systems. The idea here was that academic and industrial performers were asked to create an attack-resistant system, and Draper Labs was contracted as a red team to test just how attack-resistant these systems were. Collins' team used AADL and the research outputs of previous SEI research projects like that architecture-led system assurance and created a system that Draper was unsuccessful at attacking. And this is notable because every other system in the competition was successfully compromised. So AADL was not the only technology used, but it was sort of the architectural backbone that defined the components, gave them strict component definitions, these unambiguous statements of what was and was not intended to be in the system. And so there were fewer gaps then for the red team to exploit using their various techniques. AADL's use by both researchers and practitioners enables a really smooth transition pathway from research to practice. So you've likely heard of what's called the Valley of Death, which is the gap between academic research and industrial use. The idea that there are researchers like the Software Engineering Institute or Kansas State University, maybe Telecom Paris or Advenium Labs, that have cool ideas, and they describe these ideas using maybe mathematical statements or custom languages that a grad student whipped up and used for a couple of years. And then there are industrial users that have very concrete needs. They need problems solved. They're facing budget overruns in terms of time and in terms of cost. And so these users like the Army and Dassault have these concrete needs. But they're separated because a lot of times the research outputs are not directly usable by industry. So this is what we mean by the Valley of Death. AADL helps us bridge this valley because the researchers, in this case SEI, K-State, are using the same technology that the industrial practitioners are. So when I come up with something cool, when Jerome comes up with something cool, or a colleague here comes up with a neat idea, they can encode that in AADL, and that can be standardized and then used by practitioners. If a colleague at GTRI or at Advenium Labs comes up with a neat algorithm for model-based engineering, that can be encoded in OSATE and downloaded by the DoD and industry. We don't have to rely on someone finding our paper, understanding all the math in it, and building their own implementation. Instead, they can just use our tools the way they have been using them and get access to the knowledge that we have embedded in there. So that's really AADL's tool as sort of this bridge from research to industry that makes it such a pivotal technology and a fun one as a researcher who likes seeing his work used to work with. So now we're going to look forward a little bit and talk about the digital engineering strategy. So as you may be aware, in June of 2018, the DoD published its digital engineering strategy, and Michael Griffin wrote that the document described what the goal was, but those implementing the practices had to develop the how, or the implementation steps necessary to apply digital engineering in each enterprise. What has happened in a lot of cases is that there are a series of digital models that provide an authoritative source of truth. So think CAD or computer-aided drafting models for design. They are authoritative and can be used in a formal development process. We think that AADL can be used for the safety critical embedded systems as it is a model that supports integration, that virtual integration that I talked about earlier. It supports these formal development processes, and notably, like the second tenet in the graphic here on the right, it provides this authoritative source of truth. You can embed the knowledge that you have about your system at a given time using AADL properties, and those are unambiguous, and they can be shared with other system designers, with certification authorities, and the various types of entities that need to know various types of details about your system. We at the SEI are not the only ones that have had this recognition. Alex Boydston, that gentleman from the Army that I mentioned earlier, as well as Peter Filer, a scientist here at the SEI, and two scientists from Advenium Labs, published a document that said that the architecture-centric virtual integration process plays this key role in addressing problems with cyber-physical systems and can be this key contributor to the digital engineering strategy. So the takeaway that I hope to convey is that AADL is a tool that you can use whether you're on the more research or the more applied end of the system development spectrum. So if you want help, or if you have questions, or if you just want to learn more, please reach out. Thanks.
Hello, everyone. Welcome back again to our question, answer, and panel session. My name is again Ipek Özkaya, and I'm here with my colleagues, Sam Procter and Jerome Hughes. So, Sam, thanks a lot for the presentation. And during your presentation, there was a question that came in, which is, do you announce new embeds to downloads? So can you explain a little bit about our model of distribution?
Sure. So I'm going to interpret this question a little bit and yell at me in chat if this is not correct. But my understanding is that the question is really about, do we announce new sort of features or plugins to OSATE? And the answer to that is yes, but the sort of pipeline that moves from early research to late maturity sees different announcements of different features at different points. So if we come up with a totally new analysis or plugin, it doesn't ship with OSATE or the tool environment or even the language immediately. Instead, the language changes are circulated in the standardization committee, the AADL committee, and discussed, debated, and refined as part of that. Tooling is typically first published on some sort of experimental plugin website that you have to seek out and look for because those plugins aren't really ready for mainstream use. Accompanying that, a lot of times is an academic publication that describes the intended use, related work, and any shortcomings that we hope to address. As early adopters, use that tool, give us feedback, use the language changes, give us feedback. Then we see sort of a maturation of it. And at some point it will be pulled into the main OSATE release and announced as part of the changes that are included with every new release of the tool.
Yeah, and Patty clarified that the question was when new ideas, cool ideas are added to the AADL, and I think you exactly hit it right on. There's a process that is followed, and I think one of the strengths of the approach we have and the leadership position of the SEI is the community involvement, and it's vetted by the committee as well as standards committees before it becomes part of the overall bundle. Okay.
Absolutely. And I would just add to that if you're interested in this type of thing, we always need more participation in the AADL committee. If you see things that could be changed, the easiest time and the best time is of course early. So whether you're an industrial participant, someone from the DoD or from academia, we're really interested in your feedback on all sorts of different types of ideas. So please get involved.
So we have another question from Mr. Thomas from MITRE, and it goes, at MITRE we have developed security safety simulation tools that integrate AADL and smooth models. We would like to reach out to you, right? So this is actually, we welcome that even to us over, and let's chat afterwards. And we definitely always take on the community stuff and work with everybody that is interested. So at this point, I'd like to step back, and I'll start with you, Sam, but Jerome, please chime in. So architecting is all about trade-offs. And we talked before when we were talking with Jerome and James that there's not one model fits for all, and there are strengths and weaknesses of every single approach. But what quality attributes are best to model with AADL, and what are some of the ones that are actually excel, and are there any gaps that the community could fill in from that perspective?
Absolutely. So some of the quality attributes that have received maybe the most attention are things like the end-to-end system latency. Certain notions of scheduling within a system have been studied pretty well, have seen some use by DoD and industrial partners, and as a result, the tooling is fairly mature for that. So if you want to investigate trade-offs regarding those sort of latencies or scheduling questions, AADL is a great tool. As I mentioned in the presentation, there's also a nearly 14-year history of modeling safety related problems or questions, things like off-nominal behavior. So using the error modeling annex, these types of questions can be answered, and the trade-offs of different things can be explored there. I would also mention that a lot of people do a very sort of manual form of trade-off analysis just by modeling their systems in AADL. And even before you dive into latency specification or safety specifications, just having a high-fidelity specification of your component's interface reveals a lot of system level issues that would typically present at integration time. And so you can get a lot of good trade-off analysis there. To get back to Patty's earlier question about, where are new things announced, one of the more researchy, not ready for prime time, but very cool ideas is an automated trade space analysis tool called GATSI, or the Guided Architecture Trade Space Explorer. And this was like I mentioned, was all about the automated exploration of trade space, and used any of the plugins that come with OSATE to compare different architectures. So trade space is definitely something close to our heart, whether you're doing that manually or you want some more high-tech automated type program.
All right. Anything to add, Jerome, to that list?
Yeah, probably just also to echo some of the questions I see on the chat. So with the SEI, we are leading the technical writing of the AADL standard documents. So we have meeting quarterly. So if you want to learn more about the process, to be involved, reach out to us. We'll be very happy to tell you more about that. Especially I see the question for Mr. Thomas about this integration of Simulink and AADL. For sure, we are interested to learn more, because if it can improve the language, we'll be really interested into incorporating that. We got subsequent questions also about the adoption of AADL. So, yes, probably we can mention live that I see Rob mentioned that also on the chat, that we'll be having DoD-focused event early February that will be live, similar setting as this SEI Research Review, on the usage of AADL and AGVIP that Sam presented in the context of DoD programs, especially the Future Vertical Lift series of helicopters. What we can report is that we are still transitioning the technology, increasing the scale of TRL with a major avionics company. That for sure is a hot topic that will keep us busy for 2021 and probably for the following years.
Thanks a lot for that, Jerome. And there are a couple of questions, like, for example, what are some of the defense contractors like Boeing, Lockheed, and Northrop Grumman are doing? I think the best way to learn these actually is to attend our AADL User Day, which is upcoming on 3rd and 4th of February 2021. Sign up to our mailing list or reach out to us, and we'll definitely make sure that everybody that is interested in learn more, and more importantly, interact with the early adopters more, will be more than happy to connect and make sure that the information is shared. So I'll go to the next question from Ray. And Ray says, many defense contractors are using models superficially, if at all. How do we encourage the adoption of model-based techniques? Excellent question. So Jerome, Sam, would like to get started?
I can start on
Jerome,
this one.
go for it.
I mean, I've been involved in AADL since 2006, so it was a very long time ago. And actually, I've been on both sides of the Atlantic. For many, many years, I worked with the European Space Agency into transitioning AADL into one big project that is called TASTE, which is for the automated cogeneration from high-level models that is using AADL internally for some representations. What we have learned through this exercise is that you encourage adoption by advocacy again and again and again. And actually, it is something that happened in the mid-90s when SCADE emerged as a solution for auto-coding, again, in the avionics domain. So first, we have to do advocacy. Second, we have to build metrics to demonstrate any potentialities for return on investment. And again, there is a team working on that internal to the SEI on very specific customer project to demonstrate the return on investment. And we also have a technical report that has been published, I think, in 2018, made as part of the SAVI working group, System Architecture Virtual Integration working group as part of the AVSI consortium that demonstrated some of the potentialities for return of investment on large programs that enabled that informed a U.S. Army decision to push forward AADL even further for the next coming years.
Sam, anything to add?
No, I would just sort of echo that we have also seen the use of models superficially. It's something that we're working on. What is the best advocacy strategy? So definitely sympathize with that experience.
And I think it's a combination of challenges. One, whether the models are high fidelity enough to be able to address some of the complex challenges we have. There's that as their fidelity and capabilities increase, I think adoption challenges decrease as well. There's education aspects, and there's, of course, the processes and the cultural barriers with the acquisition lifecycle. That is a whole different slew of expertise and changes that need to happen. I think part of the getting ahead of the curve is to be able to really work parallel while we're maturing technology. We also set the right acquisition pathways and adoption strategies and learning aspects. So that's probably our best answer. We're trying to do our part with these user days as well as courses, putting our technical material openly out there, but also welcome sharing experiences, and I think we can all learn from it. So with that, I will actually go to the next question, which is kind of related, because the reality of the DoD software is legacy. We have a lot of legacy software, not all of which, most of which is not developed with model-based software engineering approaches, let alone AADL. So what is the role of OSAT in AADL to play when you have a legacy system and that was not used developed using these approaches? Is there an entry, or what might be some of the steps that an organization can take? Jerome, do you want to?
I may take that one, Ipek, if you want. The first question is, what is the objective of the modeling exercise? So in the past, we already made some investigation on that, and I think Sam mentioned the Apache example, where it was a question of modernizing an existing system, and for that do some trade-off analysis. If your objective through the modeling exercise is to get some insights about what is the trade space for redesigning a system, then you have to just realize that your modeling exercise is simply take the current system, do an abstraction, do some analysis, make an informed decision, and go back to traditional legacy software modernization. And this path is as effective as starting from scratch with a model and do the full cycle. It's really a question of having some flexible mindset so as to accept that a model is simply an intermediate step in a larger system engineering process. And with that, you can find a spot for AADL in many, many different settings.
Mm-hmm. Anything else?
I would add to that really you're modeling, whether you are modeling in sort of a greenfield type development or something more legacy related, your modeling should be driven by your objectives. So if you are having an issue that you suspect comes from jittery latency or something like that, then your model should be driven by that. And in that regard, sort of there is very little difference between modeling a system that doesn't exist and one that does, because really what you're doing is you're only modeling a portion of your system. You're modeling enough of it to get the sort of answers that you're looking for. We don't often recommend that people just model a system entirely in AADL for the sake of completeness, rather that your model should only extend far enough to get you the answers that you're looking for.
Yeah. And I think you bring up a very important point. What is the answer you're trying to get to, and how, what level of specificity? I myself have been involved in some of the exercises where latency was an issue. There were multiple organizations involved, and by being able to model that particular portion end to end using AADL or a modeling approach, we were able to zoom in into where the problem might be and then go back to the system and do the corrections. The corrections are easy often. It's really what is hard is to find where the failure is and what you would need to correct. And that's where I think these techniques can have a lot of power, even you're dealing with a system that may not necessarily be developed using some of these modern techniques from scratch. With that, maybe before we close, there were lots of questions in terms of what are some of the organizations adopting, what are their experiences. We see some superficiality in terms of using MBSE approaches. So if an organization would like to adopt these techniques, what are your recommendations? How should they get started in terms of embracing AADL and model-based software engineering?
I think that the sort of related to the answer to the previous question, really you need to go into it saying we're looking for X. We have had the best luck when we work with organizations that say, I have this problem, can AADL help us? If so, how? And in fact, some organizations have basically entirely on their own with sort of the publicly available materials about AADL taught themselves enough to get models up off the ground, analyzed those models and got the answers that they're looking for, and then either said, okay, that's enough, or expanded from there. But I would say that it is generally the best choice to go into the modeling exercise with some specific outcome in mind, and then orienting everything, training, sort of the materials you use, the amount of time you spend on it, around that answer.
Jerome, any last closing thoughts to add?
Yeah, just for it to echo that, understand what is your process, understand where you feel that AADL might be an option, and see how you can integrate it. But I would say also training and continuous training is really important. Learning AADL is a process that requires a couple of hours. I've been through that with a couple of institutions recently, with Georgia Tech, for instance. But yeah, training is of paramount importance for yourself, for your team, just so that you understand how you can improve your practice. And what we have seen through 20 years of research with AADL is that there are multiple spots where we can do it, either very specific parts or as a whole with AgVib. So we are really excited to work on that at the SEI.
So thank you very much, both. And as both of my colleagues mentioned, we have all these resources available. We have the Use AADL User Day coming up February 3-4, 2021. But I think the bottom line goes back to the more specific, your goals and objectives, especially your architectural significant requirements and what response measures you're trying to model, you'll get the most fidelity out of these techniques that we're showcasing. And there's definitely room to improve, but we've seen how well they can work when you actually can marry your goals with the available automation that is up and coming. With that, thank you both, and thank you all at the audience for streaming with us. I will close the panel, and next up will be our CTO Tom Langstaff to bring the day to a closure. Thank you all.